Hello, in this video I'd like to talk about structure-preserving maps. These are functions from one structure to another. They take in elements of one structure and output elements of another structure in a way that, if those elements are related to each other in a particular way before applying the function, and then we apply the function to them, they're going to stay related in that particular way. As a very basic example, imagine that you're trying to do some addition problem involving Roman numerals. You could use the rules for adding Roman numerals together, which are quite complicated, or you could translate from Roman numerals to Arabic numerals, and then add using the Arabic numerals, and then translate back to Roman numerals, and this process would be easier. And the reason that this process works is because when we take two numbers and add them together and then translate the result, we get the same thing as if we were to translate the two numbers and then add the results. This motivates our definition for a monoid homomorphism. A monoid homomorphism is a function, f, that takes in elements of one monoid, m. So here I'm going to denote the operation of the monoid by this circle, and we're going to denote the identity element of the monoid by e sub m. And it's going to take in elements of m and output elements of n. N is a monoid with this star operation and an identity element which we're going to call en. And we're going to require that if x and y are elements of m, and we combine them in m, and then translate the result over to n using our function f, that's the same as if we were to take x and translate it over to n, and y and translate it over to n first, and then apply the operation to them. We'll also require, just to keep things nice, that if we translate the identity element of m, we wind up getting the identity element of n. This doesn't fully capture our notion of translating back and forth between Roman numerals, however, because our function f is only a one-way translation. It doesn't tell us how to get back from n to m, and in fact the function might take two different elements and map them to the same element, so we can't undo. So this function goes from being a homomorphism to what we call an isomorphism if it's a matching between elements of m and n, such that you can undo that matching. We require that f is 1 to 1. This is as opposed to being many to 1. We had our example here where we have two different elements of m that get mapped to the same element of n. This is a many to 1 function. Many different elements of m are getting mapped to the same element of n. That's not what we want, because we want a pairing between m and n. We want it to be the case that every one element of m gets mapped to one element of n. And we also want to require that our function f is onto, that is, that every element of n winds up getting mapped to by something. Again, we're trying to pair up the elements of m and n to say that this is the translated version of this. This is the translated version of this, and so on and so forth. And if this isn't the f of something, then we can't say that it's the translated version of something. So we need some element of m to map to it. That is, we require all elements of n to be mapped onto. So if f is in fact such a pairing, such a matching between elements of m and elements of n, we call it an isomorphism. And really what we're doing is we're looking at exactly the same situation we were with Roman and Arabic numerals. We just had different names for what are fundamentally the same thing. Because we can think of isomorphisms as just renaming the elements of a structure, it means that any logical property that the one structure satisfies is also going to be satisfied by the other structure. Remember that model theory is the study of what first-order properties are satisfied by what structures. Of course, these isomorphisms can still be very non-trivial. For instance, the exponential function, which takes in a number x and outputs e to the x. This is the notation for f of x is equal to e to the x when we're trying to write it in parallel of saying that this function takes in inputs from here and outputs to here. The function f of x equals e to the x is an isomorphism between the monoid, which is the real numbers under addition, of course the identity element there is 0, to the monoid of positive real numbers under multiplication, and the identity element there is of course 1. You can check that when we translate this equation here so that it uses the operation of the first structure here and the operation of the second structure here, we get the basic rule of exponents, that e to the x plus y is equal to e to the x times e to the y. You can check that this function doesn't map two different numbers to the same number, and it maps onto all positive real numbers. Every positive real number is e to the x of some real number. Because of that, we have an isomorphism between these two structures. And because of that, we know that any first-order logical property that's true of one structure is also true of the other structure. So for instance, because addition is commutative over here, we know that multiplication has to be commutative over here. Generally speaking, we want our homomorphisms to be onto. Let's take a look at a monoid homomorphism that isn't onto. Here we have the identity function, so f of x is equal to x, mapping from the natural numbers with addition and 0 to the integers with addition and 0. You can check very easily that this satisfies these two properties of monoid homomorphisms, but this doesn't really let us translate properties of the natural numbers to properties of the integers. It really just tells us things about a specific subset of the integers, specifically all of those things that get mapped to by this function. We call this the image of the function or the range of the function, the set of all possible outputs. That's going to form a substructure of this structure here, and that's really what we're finding out about when we study the properties of the natural numbers. On the other hand, it is really useful to study monoid homomorphisms that are onto but aren't one-to-one. In some sense, these functions lose information, and that just happens because the function is not one-to-one, right? If we have two different elements of m, and they get mapped to the same element of n, we've lost information. When I tell you that f of x is equal to this element here, you've lost the information about whether x was this element or this element. For instance, the squaring function, if I take a number and square it and tell you that the result is 9, you can't work out whether my original number was positive or negative 3. You retain the information about the magnitude of my original number, but you've lost the information about whether it was originally positive or negative. For instance, we can have a function mapping from the monoid of words under concatenation to the monoid of natural numbers under addition that just takes the length of each word. It might help to go back to the definition of monoid homomorphism and convince yourself that this is in fact a monoid homomorphism, that it really does satisfy the properties that I've said that it does. This monoid homomorphism is onto every natural number is the length of some word, but it's not one-to-one. There are many words that have the same length. So in some sense, we've lost information. We originally knew all of the letters in the word, and we've lost that information. We no longer remember what letters were where, we just remember the length of the word. Another really good example for seeing this losing information phenomenon is to take a look at the projection onto the first coordinate function, which takes in a vector from R2, so a pair of real numbers, and we're considering this a monoid under addition with the identity element 0, 0, and outputs just one real number, specifically the first element of the pair. Again, you can check that this is a monoid homomorphism, and it's onto, but it's not one-to-one. Here we've retained partially some of the information about the original input. Specifically, we've retained its first coordinate, and we've completely lost its second coordinate. There are lots of really natural monoid homomorphisms out there, such as the evaluation at pi function, which takes in a polynomial, so the set of all polynomials under addition forms a monoid. It takes in a polynomial with real coefficients and outputs a single real number. And it does so by taking the original polynomial and plugging pi into it. Again, it might be helpful to verify that this is in fact a monoid homomorphism. Note that there's nothing special about pi, and in fact there's nothing special about the fact that we're looking at polynomials. You can do this with any set of formulas on a single variable, and actually multiple variables if you want to evaluate at x equals pi and y equals e and so on and so forth. There are also some weirdly artificial monoid homomorphisms. For instance, the isitpositive function, which takes in a natural number and outputs an element of this monoid here. So this monoid has two elements, 0 and 1, and the operation is to take the maximum of, so if you have a and b, to combine them together, you take the maximum of a and b. And you can check that this is in fact a monoid, and its identity element is in fact 0. So the ispositive function takes in a number x and outputs 0 if x is equal to 0, and outputs 1 if x is positive. You can check that this does in fact satisfy the properties of being a monoid homomorphism. We can also apply a lot of tricky functions on the word monoid. So for instance, we could have the just a and b function that takes in a word on the alphabet A, B, and C on that word monoid under concatenation, and outputs a corresponding word which is just the instances of A and B in the original word in the order that they show up. So it gets rid of all of the C's, and we're left with just whatever's left over in terms of A's and B's in the same order. And you can verify that this is in fact a monoid homomorphism. Given a particular deterministic finite state automaton, we also have the example of a function from words to functions from the set of states to the set of states under composition. The set of all functions on a particular set form a monoid under composition, with the identity element being the identity function. And this monoid homomorphism takes in a particular word, W, and outputs the action of W on Q. Remember that our words act on the set of states. We can treat them like functions on the set of states. That is, that if you type in a particular word, it takes the state that you started out in when you started typing that word to some other state, the state when you finish typing that word. This creates a function from states to states, and that's what we call the action of W on Q. And so we can turn words into those corresponding functions. And again, you can verify that this function here is a monoid homomorphism. It's worth noting that this isn't necessarily an onto monoid homomorphism, but it's such an important example because it draws this connection between monoid homomorphisms and regular languages. The language recognized by our finite state automaton is exactly the set of words that get mapped to some function that takes in the start state and outputs an end state. There's lots of such functions, and any word that gets mapped to one of those functions is in our language. In some sense, our language is the set of all things that get mapped to this specific set of functions, the specific subset of this structure here. In other words, it's the pre-image of that subset of the structure. And in fact, this characterization of the regular languages is exact. So if we have some sort of monoid homomorphism from the word monoid on some finite alphabet to any finite monoid, and we have an arbitrary subset of that finite monoid, then the pre-image of that arbitrary subset, that is the set of all words such that f of that word, when we run it through this monoid homomorphism, is in that subset, is going to be regular, right? This is a set of words, and it's in particular going to be a regular set of words. So specifically, we construct a deterministic finite state automaton whose states are elements of M, and we construct the transition function for this finite automaton, where if we're in a particular state M and we read the character C, the result is going to be we take C, that's a character, but we can treat it as a word. We run it through this monoid homomorphism. That's going to give us an element of M, and we just multiply the current state by that element. Then you can check that f of w is just going to be the state that if we started off in the start state and we read the word w, that we'd wind up in, right? F of w is an element of the monoid, so it's going to be a state of the finite state automaton, and it's in particular going to be this state, the state that we get to starting in the start state, reading in the word w. And so if we turn n into the set of accept states, then this set here is exactly the set of words that are accepted by this finite state automaton. So this gives us a bit of an esoteric characterization of the regular languages. Specifically, they're the pre-images of some set under a monoid homomorphism from the word monoid to a finite monoid. And these are exactly the regular languages. But of course, we're not just interested in studying homomorphisms and isomorphisms for monoids. We're also interested in studying homomorphisms and isomorphisms for arbitrary structures. We've already seen in the monoid case what it means for a function to preserve a binary operation and a constant. If we have a function from one structure M to another structure N, and we have a binary operation in M and N, then we say that the function f preserves or respects this binary operation if, when we apply the operation in M and then translate, that's the same as translating first and then applying the operation in N. We also saw what it means to preserve or respect a constant. That is, if we take the constant in M and we apply our function to it, we wind up getting the corresponding constant in N. So in the monoid case, this was the identity element, but there's lots of other constants that you could want in any particular structure. What about if we have a unary operation? We've seen a number of structures that have unary operations, usually successor operations. So they take in one input and they output an element of the structure. Another example of a unary operation is negation. And here, M and N might have slightly different notions of negation, and we say that this function respects that notion of negation if, when we negate in M and then apply our function, that's the same as applying our function first and then negating in n. And generally, if we have an operation, let's call it s, we say that f respects s if when we apply the operation first to a bunch of elements of m and then translate over to n, that's the same as translating over all of the elements first to elements of n and then applying the operation in n. Just like in the monoid case, these operations might be very different from each other, but because there's a structure-preserving map from one structure to the other, they're going to be at least a little bit similar in their properties. We've also seen some structures with binary relations. We've seen both less than or equal to and in. Here we say that a particular function from one structure M to another structure N with separate notions of what it means to be less than or equal to in those two different structures, if whenever x is less than or equal to y within M, then f of x is less than or equal to f of y within N. So if we start off with two elements where one is less than or equal to the other in M, and we translate them over into N, the resulting elements are still going to be less than or equal to each other in the respective order. You might recognize this property. This is what it means for a function to be increasing, although not strictly so. Structures can also have other sorts of relations to them, either unary relations that take in only one input, or perhaps a relation that takes in lots of different inputs. And we say that a function f respects this relation R if whenever we have a bunch of elements of M that are related to each other by R, the notion of R in M, then when we translate them over to N, they're going to be related to each other by N's notion of R. If you think about it, this is actually kind of a strange definition, because it may be the case that the notion of R within M is fairly intricate. There's a bunch of tuples that satisfy this relation, and there's a bunch of tuples that don't. And it could be the case that the notion of R in N is always true. Every tuple satisfies that relation. Then this implication is trivially true. Of course it's going to be the case that whenever R holds of some tuple in M, R holds of the image of that tuple in N, because R always holds in N. Shouldn't we require an if and only if? Shouldn't we require a closer connection between the notion of R in one structure and the notion of R in another structure? How does it make sense to say that this function is preserving that structure? Well, first of all, if we're talking about isomorphism, we do want these to be if and only ifs, right? If we're saying that everything that's true in M is true in N, that M and N are really the same thing, just with things being renamed via this translation function, then we really do want it to be the case that some relation holds in M if and only if the relation holds of the corresponding elements of N. So if we're talking about isomorphisms, then this condition does need to be if and only if. On the other hand, if we're just interested in a homomorphism, if we're not interested in a function that pairs up the elements of two structures, if we're interested in a function that just goes from one structure to another, well, let's actually take a look at a binary relation that all structures have: equality. For an arbitrary homomorphism, we simply require that if x is equal to y, then f of x is equal to f of y. This is just what it means to be a function. But we don't require the reverse. It could be the case for a homomorphism that we have two separate elements of M and they get mapped to the same element of N. In that case, we have f of x is equal to f of y, but we don't have that x is equal to y. So this implication is not true in the reverse. It's only the case that when we start looking at isomorphisms that we require this to be an if and only if. In an isomorphism, we require that x is equal to y if and only if f of x is equal to f of y. In other words, the function is 1 to 1. So based on this binary relation that we already kind of had to have work this particular way, we define what it means for a binary relation to be respected or preserved by a particular function, depending on whether we're looking at a homomorphism or an isomorphism in the corresponding way. Let's take a look back at our monoid homomorphisms to see what other operations and relations they wind up preserving. For instance, our e to the x function from the reals to the positive reals winds up also preserving order, because e to the x is a strictly increasing function. This function also satisfies the property that exp of half of x is equal to the square root of exp of x. So if we add in half as an operation here, and square root as an operation here, and we view these two operations as different instances of the same sort of thing, then that thing is being preserved by this map. Another way that we say this is that the exponential function takes the half operation to the square root operation. Because e to the x is continuous, we say that it also preserves limits, but limits are not a straightforward first-order logical operation, and so you need to add a bunch of other equipment in order to be able to view them that way. Our length operation can be viewed as preserving successors. We have notions of successor A and successor B and successor for whatever letters within sigma star, and all of those successor operations wind up being taken to the successor operation on the natural numbers. Our evaluation at pi homomorphism actually winds up respecting the entire ring structure of the polynomials. That is, it respects addition, multiplication, and subtraction, and the constants 0 and 1. And if we were to expand the domain for this evaluation function, it would wind up respecting any operation or constant that you could come up with. The evaluation homomorphisms are some of the most structure-preserving maps out there, and in fact we can view homomorphisms from the word monoid to arbitrary monoids as evaluation homomorphisms. Here we treat a word as an expression with some variables in it. We treat these different characters as variables that represent different elements of our monoid. In particular, A is going to represent whatever f of A is under this operation, and B is going to represent whatever f of B is under this operation. And so AB, BAB is going to represent whatever we get when we plug in those values for A and B in this original formula, and then combine them using the monoid operation. The isPositive function also preserves less than or equal to, but not less than. So it is the case that x being less than or equal to y implies that the isPositive version of x is less than or equal to the isPositive version of y, but this doesn't work if we get rid of these equal to signs. Then this doesn't hold. This function also takes multiplication to minimum. And finally, it's worth noting that if a function preserves not equal to, then it has to be 1 to 1. This is what it would mean for a homomorphism f to preserve not equal to, and we see that this exactly is the definition of what it means for a function to be 1 to 1. So So one of the questions we might ask is, for isomorphisms, we know that any logical formula that's true of one structure is true of an isomorphic version of that structure. But what do we know if there's a homomorphism from one structure to another structure? It's not necessarily going to be the case that these structures are identical to each other, but they're still going to share a number of logical properties in common. What logical properties are necessarily shared in common, and what logical properties might they differ in? We say that a formula is positive if it is made up out of atomic formulas and or, and the quantifiers for all and there exists. Specifically, we're missing out on not and implies, and I guess if and only if. We just have and or for our Boolean connectives. So it turns out that if a formula is positive, then it's preserved by onto homomorphisms. So suppose that we have a homomorphism from one structure M to a corresponding structure N, and this homomorphism is onto. That is, there's nothing in N that isn't getting mapped to. Then if our formula is true in M, the translated formula is true of the translated elements in N. We prove this fact by induction on the construction of the formula. For atomic formulas, this is the definition of what it means to be a homomorphism. If we know that one formula, phi, is preserved by onto homomorphisms, and another formula, rho, is also preserved by onto homomorphisms, then we know that phi and rho is also preserved by onto homomorphisms. Because if we know that phi and rho is true in M, that tells us that phi is true in M, and so phi is true in N, and rho is true in M, so rho is true in N, and so therefore phi and rho is true of the translated elements in N. A similar proof works for or. If we have a formula that's true for every x in M, it's also going to be true of every translated version of x in N by this property. And so provided that our function is actually onto, it's going to be true of every element in N. On the other hand, if there exists an x in M making a particular formula true, then the translated version of that x is going to make the translated formula true. And so hopefully that gives you a sense of how this proof by induction on formulas works. This fact is in fact exact. If we have a formula that is preserved by onto homomorphisms, then it can be written as a positive formula. The proof of this is a little bit more complicated, and I'll link to a source down below. If we take the contrapositive of this fact, it tells us that if a property is not preserved by onto homomorphisms, then there's no way of writing that property as a positive formula in the first order logic. For instance, if we look back at our onto homomorphism length, which goes from the set of words under concatenation to the set of natural numbers under addition, we notice that the set of words under concatenation is not commutative. That is, the order that you concatenate two words in can matter. Lengths, however, are commutative. If we add together two numbers, it doesn't matter the order that we add them together in. And so this tells us that there is no positive first-order logical formula that expresses that a structure is non-commutative. If we take a look at our is-positive homomorphism from the natural numbers with addition to the set 0, 1 with the maximum operation, we notice the fact that the first structure is countably infinite is not preserved by this function. And so that means that there's no positive first-order logical formula expressing that a structure is countably infinite. In fact, there's no first-order logical formula at all that expresses that a structure is countably infinite. This homomorphism also doesn't respect the cancellation property. In the natural numbers, if x plus y is equal to x plus z, then y is equal to z. On the other hand, in our 0, 1 with maximum structure, this is not true. And so that tells us that we can't express this cancellation property as a positive first-order logical formula. Somehow, having this implication here, or a negation somewhere, is necessary. I don't think this fact will come up later in our video series, but I wanted to show it off because it forms a real connection between syntax and semantics, a common theme within model theory. Here when I use the word syntax, I'm talking about the internal structure of our formulas. In this case, our definition of what it means for a formula to be positive is an assertion about the internal components of that formula. We're saying that within the structure of that formula, there are no negations or implications. And so this is a real syntactic property of a formula. On the other hand, saying that a property is not preserved by onto homomorphisms doesn't really depend on the internal construction of the formula. It really only depends on what the property is saying. What sorts of things is the property true of, and what sorts of things is the property false of. We only care about the meaning of the property and not the internal components of the way that it's written. In this case, we say that we're only concerned about the semantics, or the meaning of the formula. And so this connection between syntax and semantics, if we restrict what sorts of formulas we're allowed to use, what sorts of things can we say, what sorts of things can't we say if we restrict what sort of formulas we have, these sorts of questions are the kinds of questions that model theory likes to ask. On the other hand, model theory doesn't concern itself too much with functions from one structure to another. Functions from one structure to another allow us to capture the size of structures. We know that if two structures can be paired up so that every element of one structure is paired up with a corresponding element of another structure, we know that these two structures have the same size. And so by working with functions between structures, we can talk about the sizes of those structures. On the other hand, first-order logic isn't capable of expressing sizes, isn't capable of expressing that a particular structure has a particular size, or that there are a particular number of elements that satisfy a particular formula. Except in the case where there's like 5 elements, and then we can say, oh, there exists an x, y, z, w, and u, and anything else is one of those 5 things. But if we're talking about infinite cardinalities, then first-order logic is completely useless for expressing these things. So we don't concern ourselves with functions from one structure to another particularly often, but this is a really important way of studying structures, and it will come up in the next video. If you're interested in studying structures based on what sorts of functions we have going from other structures to those structures, you might be more interested in studying what's called category theory. So thanks for watching. Please leave a comment down below if you have any questions or comments about structure preserving maps, and I hope to see you in a future video.